And thank you, Robert, for putting the whole entire DDN roadmap strategy into context, and it really is an end-to-end story. I'm going to dive into one part of this, the IME part of it, and what we're demonstrating here at ISC, and knowing how this fits into the larger context of DDN's portfolio or product strategy is very helpful. So you've seen in the slides up in this morning, you've seen reference to I/O provisioning and performance provisioning and storage. And I think when we get done talking about what DDN is doing with IME and what we're doing on the showroom floor, I think you'll come to really appreciate that phrase more. Traditionally, we've always thought of storage as something where you get the performance and the capacity are all in one thing. You buy a disk and it has a fixed capacity and it has a fixed bandwidth. If you want more bandwidth, you would buy more of those devices, and along with it, you would get more capacity. And from an architect perspective, or as you're architecting a system, there was always this fixed relationship between capacity and performance. And by adding a tier of SSDs or flash or non-volatile memory in between where your compute happens and where your persistent store happens, what you're finding is that there's a lot more control that you have over architecting and balancing your capacity versus your performance, and it really becomes a performance provisioning exercise, and not just buying, how many devices do I need to put into the box. And so coming from this, and we'll talk about with the demo, I/O acceleration, scalability of applications, and most importantly, how these things really result in data center efficiency and cost savings for you. So what is a burst buffer, and how are we implementing IME initially as a product offering for the HPC environment? And we're doing so in the form of what we call a burst buffer. And so you can think of a burst buffer as this tier of storage highlighted by the red box here that is really fitting in between where the compute nodes are and where the persistent storage is. And so the idea is that we want you to be able to read and write memory into your compute nodes as quickly as possible from flash instead of to go out to a parallel file system. But let's stop and ask, why is this important and what's driving us to this architecture? There's very clear reasons why we're doing this. So I can use data that one of our partners, Argonne National Lab, shared with us about one of their production environments. And the numbers are actually quite sobering. They tell us that 99% of the time, they're only utilizing 1/3 of the peak bandwidth of their parallel file systems. And even more interestingly, 70% of the time, they're only using perhaps 5% of the peak bandwidth of their file systems. And this often comes back down to this issue of, are they using the system for capacity? Are they using it for bandwidth? Sometimes they're using it for one and not the other, and they're not able to dial in precisely what they need in terms of capacity and bandwidth for their workload. So the idea behind a burst buffer is to add a tier of flash memory where we can absorb bursts of I/O, which therefore lets you have a parallel file system capability that is more targeted to your sustained I/O requirements at your data center, and not architecting your parallel file system to address the peaks. So we're taking the peaks off of your bursty I/O and handling that inside of a burst buffer. And so if you really think about it, how fast does a burst buffer need to be? Well, it depends on how large of that peak you want to absorb. What's the capacity that you need your burst buffer to be? And that's often determined by the period in which you want to absorb the burst and maintain that inside of the burst buffer. Some interesting guidelines that we have found in talking with many customers about their workloads and their I/O requirements is that often the capacity of a burst buffer in the HPC environment, the capacity naturally might be maybe 3 times the aggregate memory of your supercomputer as just a starting point. You always ask, okay, where do I start? And then we can refine the number from there. So 3 times your aggregate memory. And the bandwidth is very configurable. It really is not a limitation of the software, the IME software, but rather it's really a matter of how you wire up your burst buffer. But again, another guideline is often customers find that they would like to have maybe 10 times more bandwidth into the burst buffer than they do into their parallel file system, a 10-to-1 ratio. And then again, that's a starting point for how do I size a burst buffer for my system. And so one other thing that's important to note is that IME, Infinite Memory Engine, is an implementation where we have a very thin client running on the compute nodes, and then we have a server function that's running inside the burst buffer appliance. And the interface between the compute nodes and the burst buffer is not POSIX. It's a very high performance, very low latency interface upon which we have implemented POSIX. It's something that we allow to be mounted like a standard file system. We've written custom interfaces for MPIO, for example, and so we're able to provide you the interfaces that you're accustomed to, but we're not relying on POSIX, and therefore we're not held back by limitations of POSIX like file locking and whatnot. And that really is the secret here, is breaking the barriers to what POSIX is holding us back on in terms of file locking and other limitations. And so it really does give us an unbounded performance opportunity. So when you see in our booth and around the conference, you see things like scale memory to hundreds of terabytes, 50% less latency than an all-flash array, 1,000x bandwidth application performance improvements. Those are very real numbers, and so let me explain to you what we're doing in our booth as a quick overview of the demo. And I do encourage you to stop by the booth and talk to the engineers and see it for yourself. So in the booth, we have a setup of a number of compute nodes, 8 servers, IME servers, which in each of those IME servers is really just a 2-processor Xeon box with a whole bunch of SSDs in it running our IME software. And part of the demo system is also parallel file system. In this case, we're using GPFS. We could likewise use Lustre. We could even just use NFS if we wanted to. And so the peak capability of this demo setup is 80 gigabytes per second that we can read and write into the SSDs from compute nodes, 3 gigabytes per second to the parallel file system, and 20 million IOPS in this configuration. So that's the peak capability of the hardware setup. And then you ask, okay, well, what happens when I run a real application on this setup, and what types of speedups are we getting? So we're running S3D. It's a turbulent combustion simulation, for those of you not familiar with S3D. I don't have time to go into the details of what science is going on in the application, but it is a multidisciplinary application. We're doing chemistry in addition to a lot of turbulent flow simulations. If you look at the performance that we're able to see on this very complex, very real HPC application, what you can see is that we're driving the peak bandwidth from the application into the burst buffer. We're actually driving things at line rate. We are getting peak performance out of the hardware. An interesting thing to note, though, is that if we run the same application with no changes, we can either run it using the burst buffer or we can run it without the burst buffer. The changes are done at the system level, not at the application level. If we run that same application and have it write directly to the parallel file system, we're only really seeing less than 50 megabytes per second of I/O. In other words, 4K strided I/O. It's really ugly I/O that this application naturally wants to do, and it can bring down any parallel file system on any system. And so by inserting the burst buffer, what we're able to do is to achieve very high-speed performance. We're breaking away from file locking and other constraints that POSIX brings to us, and doing a 1,000x improvement in bandwidth on this very real application. And then the real magic here, that's interesting. We're able to write to SSDs at line rate, and the IME software manages the coherency of this data. But the real magic also comes into play when we replay that data from the burst buffer into the same parallel file system. Because inside the burst buffer, we can realign the data, we can coalesce data, we can do a lot of rearranging of the data sets. We can actually drive the parallel file system also at its peak performance, because we're able to align the data to achieve the optimal performance. And so what the real story here is driving efficiency out of the hardware that you're buying. And the real story is disaggregating the capacity requirement from the bandwidth requirement by tuning in the right bandwidth and capacity of a burst buffer, and then having very intelligent software, in this case IME, that is managing that interface between the application and the parallel file system. Phenomenal results on a very real HPC application. I compel you to stop by the demo in our booth and to speak with the engineers and see it for yourself. And so, as Robert indicated, there's some very real claims that we're making here. These are very important aspects to architecting I/O in your supercomputers into the future. And it really comes down to getting more performance, being able to tune in more performance into your system without simply buying more hard disks, and being able to decouple those two issues of performance and capacity. And a lot more of the details that Robert covered very well in his view. You can see how IME is one small piece to an end-to-end solution that DDN is driving. And this one little piece in and of itself is very compelling, has very direct impact to your workloads, to your application performance, to how you architect your systems and how you manage your systems in the future. So please stop by our demo. I encourage you to do that.